So we needed to finish up section 6.1. So where we're going to start is with interval notation. So you know what interval notation looks like because you've used it in previous courses. And we've used it a lot of times when describing where a function exists. And for example, its domain, or perhaps its range. So we're going to formalize interval notation in set notation. So if we are given a real number a and b, where a is less than or equal to b, then we can define from a to b, with parentheses on both sides, as being the set that says x is a real number such that x is between a and b. Or on our number line, we have a and we have b. We have an open circle at a, we have an open circle at b, and they're connected. This changes a little bit if we put a bracket on either or both sides. So for our next interval, where we have a to b, but we're including both a and b, we describe that as the set x is a real number such that a is less than or equal to x, which is less than or equal to b. So at a, we have a filled in circle. At b, we have a filled in circle, and they're connected. We can also mix and match for our a's and b's. So I did that for the next two intervals, where we have a not being included, but b is being included. So parentheses with the a, bracket with a b, means that x is a real number such that a is less than x, which is also less than or equal to b. So we are open at a, we are closed at b, and still connected. I flipped it around for the fourth one, where I said, well, let's be closed at a because a is included, but open in b because b is not included, and we're still connected. So what happens if I go from a to infinity? Well, in that case, I start at a, and a is not included here, so it's open, but it's going off to infinity, so it just keeps going off to the right. If I include a and still go off to infinity, I have a closed circle and still going off to the right. Might be easier if I add another layer of red in there to make it easier to see. On each of these, there you go. That makes it a little easier to see where we're connected. Now we never ever include infinity or negative infinity with a bracket because you can never actually stop there because it doesn't end. So it will never be, you'll never be able to literally stop on infinity, so we will never have it included with a bracket. So you'll notice when we look at the seventh one here, we have negative infinity to b, and the eighth we also have negative infinity to b. For the seventh, b is not included, and for the eighth, b is included. And these go all the way down to negative infinity. So knowing that we can represent inequalities and interval notation in set notation means that we can also perform operations on inequalities and intervals like we do other sets. And that's where we're going with example 6.1.6. For example 6.1.6, we're going to let U, the universal set, be the set of all real numbers, and we're going to let set A be the interval from -1 to 0, not including -1 and including 0, which is defined as the set where x is a real number such that the -1 is less than x is less than or equal to 0. And B is the set that is given by 0, which is included, to 1, which is not included, which is given in set notation as x is a real number such that 0 is less than or equal to x, which is less than 1. We want to find A union B, A intersection B, the difference of B and A, and the complement of A. So before we can do any of that, we're going to draw sets A and B on number lines. So set A does not include 1, so it's open at -1, sorry, -1, not 1, and it is closed at 0. So we have a set that looks like this. For set B, we have included 0, but we do not include 1. So we have a set that looks like this. So we want to find first the union of A or B. What that means is I want all values that are included in set A or in set B. Well, we already know if we just come straight down, we know that we don't include 1, but we include everything up to 0. Well, the next one includes everything from 0 up to 1, but doesn't include 1. So there is our union. And if we want to write it in set notation, we would say that A union B is the set where x is a real number such that -1 is less than x, which is also less than 1. So if we wanted to do the same thing, but now for A intersection B, we're looking at what both sets have in common. So you'll notice set B has nothing before 0, so we can't include anything from set A that's before 0. But set A has nothing after 0, so we can't include what's after 0 from set B. So the only thing these two sets have in common is literally just 0. As strange as that might sound, it is okay to have a set that only has one element. And in this case, if we wanted to write it in set notation, we would say A intersection B is the set where x is a real number such that x equals 0. X equals 0 is the only element of our set. So now, let's try finding something a little bit more challenging. Let's find the difference of B and A. So if you remember from our last class, that means we want to take everything that is in set B and we want to remove from that any element of B that is in A. So if I look at set B, we just figured out that literally the only thing in B, the only element in B that's in A is 0. So all I'm going to do is take set B here and remove 0, which is the same as emptying the circle at 0. So we're going to have an open circle at 0 and an open circle at 1, and it's still connected. So if we were to write this in set notation, we would say that B minus A, the difference of B and A, is the set where x is a real number such that 0 is less than x, which is also less than 1. We have one more property that I wanted to look at, and that is, what is the complement of A? Well, if you remember, by definition, the complement of A is every element that is in the universal set that is not in A. So it will be all real numbers that are not in A. Well, what does that look like? It looks like at -1, we are filled in. We can't go to the right yet, so that part's going to have to go to the left. We can't include anything between -1 and 0. We can't include 0, so we now have an open circle at 0, but then we include everything past 0. It is literally anything not in A. What does that look like in set builder notation? Well, A complement would be the set of, whoops, started to write something wrong. Set where x is a real number such that -1 is less than x or x is greater than 0. We could do the same thing to find B complement, even though I didn't have it drawn here. B complement would have an open circle at 0 going to the left and a closed circle at 1 going to the right. It would look very similar to A complement. For example 6.1.7, we're going to describe in words what the sets are that are listed. For part A, we have D is the set where x is a real number such that 3 is less than x is less than 2. So what that means then is that D consists of all real numbers that are greater than 3 and less than 2. If you think about it, can you think of a single number that's greater than 3 and less than 2? If you do, I think we can make $1 million together if you can prove that there really is such a number without having to improve or invent a new numbering system. No pulling a Sheldon. So, since there are no real numbers, right? Since there are no real numbers that are both greater than 3, oops, there's an E in greater. Let me fix that. Sorry about that. There we go, that are both greater than 3 and less than 2. D has no elements. Oops, that's supposed to say no. D has no elements. Therefore, D is actually the null set. Let's see if we fare any better in E. E says that I have a set where x is an integer such that 2 is less than x, which is also less than 3. Well, if we were talking real numbers, this set would have elements because it would be all of the real numbers between 2 and 3 that don't include 2 and 3. However, the domain that we gave x this time is the set of integers. There are no integers between 2 and 3. Right? So E consists of all integers between, but not including, right? Between, but not including 2 and 3. So we would say since there are no integers that are both greater than 2 and less than 3, E has no elements. So we did not fare better in this one because that means E is also the null set. For the last topic in section 6.1, we're going to be looking at partitions and power sets. Before we can define a partition, we have to define what it means to be disjoint. Two sets are called disjoint if and only if they have no elements in common. So A and B are disjoint if and only if their intersection is the null set. Sets 1, 3, 5 and 2, 4, 6 are disjoint because their intersection is the null set. Right? A intersection B here is the null set. A group of sets is a partition, so this is another new term. A group of sets is a partition of set A if the union of the sets A sub I, so each of the subsets of A, creates A, and the intersection of all the subsets A sub I is the null set. So if we were to have n subsets of A, then we would say then that A will be made up of A1 union A2 union A3 union ... all the way out to a union with A sub n. And likewise, A sub 1 intersected with A2, with A3, with ... with AN would be the null set. And here's the other requirement for a partition is that each of the sets has to be mutually disjoint. Any two sets, so any two subsets must also be disjoint. So all of these subsets A1 to AN are mutually disjoint, or as our business friends like to call them, mutually exclusive. So if we let A be PQR 6, 8, where A1 is PR and 6, and A2 is Q8, then they make a partition because their union makes up A, but their intersection is empty. So if you think about it, essentially what we're doing is we're taking this big set A and we're breaking it into pieces. Here's A1, there's A2, maybe there's A3, A4, and A5 and A6. And what we want for them, if they make a partition, is literally to not cross over at all. So that means that they share not one single element. So that way, the intersection of A1 and A6 is null. A3 and A2 is null. A4 and A5, it's null. Any two subsets, their intersection is null, but the union of all the subsets together should form A. That's how you know you have a partition of A. One other property of sets is a power set. So if we're given set A, the power set of A, which is this funny looking P of A, is the set of all subsets of A. So if we let, as an example here, we're going to let our first set A be 1, 2, 3, 4, 5, and 6. We're going to define subset A1 as 1, 2, subset 2 is 3, 4, and subset 3 is 5, 6. Is A1, A2, A3 a partition of A? Well, let's see. Is 1, 2, union, 3, 4, union, 5, 6 equal to A? Well, that union would be 1, 2, 3, 4, 5, 6, which is A. So first step down. Is 1, 2 intersected with 3, 4, intersected with 5, 6, the null set? It sure is. And in fact, A1 intersected with A2 is null. A1 intersected with A3 is null. and A2 intersected with A3 is also null. So in fact, yes. So yes, the set A1, A2, A3 is a partition of A. Now, our second part of this question asks, does A1, A2, A3 make up the full power set of A? And that answer would be no, because A1, A2, and A3 as a set doesn't include, for instance, the null set, or just one, or just two, or dot, dot, dot. There's a whole bunch more. There are a lot of missing subsets. If we wanted to look at a power set that we could define all the subsets of, let's look at something like if I gave you this set A, B, C. The power sets here of, oh, let's call this set B. The power set of B would look like the set that includes the null sets, a set of just A, a set with just B, a set with just C. So those are all of the one element sets. Then we would have two element sets. So A and B, A and C, and B and C. And then lastly, we would have the set that includes all three, A, B, and C. That is the power set of set B.